Next topic, sequence. Monotonic sequence. We define first of all monotonic sequence. Monotone. So a sequence Sn is said to be monotone increasing if Sn plus 1 is greater than Sn for all the natural numbers. Sn plus 1 term n plus 1 term is greater than Sn. That is what, if you put here n equal to 1 natural number, S2 greater than S1. If you look n equal to 2, suppose S3 will be greater than S2. Okay, and so on. So if you arrange, then S1 will be less than S2. S2 will be less than S2. S2 will be less than S3. S3 will be less than S4. Okay, so bigger terms are S1 smallest, S2 bigger is increasing. Okay. In this way. Okay. It's a graph. Okay, here S1, okay, S2, S3, so increasing. Graph increasing. Second equation, decreasing. A sequence Sn is said to be monotonic decreasing. Now this change are now. Sn plus 1 will be less than Sn. Sn plus 1 less than Sn. Means if you put n equal to 1, suppose S2 will be less than S1. If you put S equal to 2, suppose then S3 will be less than S2. Okay? And so on. So what is here? S1 will be greater than S2. S2 will be greater than S3. Okay, so first term biggest, then smaller and smaller and smaller. Okay, graph now is like decreases. S1 here biggest, S2, S3, so graph forward decreases, increases, bigger. Know this by definition, this one Sn plus 1 greater than Sn, increasing. Sn plus 1 less than Sn, increasing and decreasing. Next, okay, we define bounded sequence. Bounded sequence. Bounded definition: a sequence Sn is said to be bounded if there exists a positive integer number K suppose, such that mod of this Sn will be less than K. Like function, sigma is what? Function. Bounded function, Sn less than K, less than K. So mod of Sn less than K, or also the definition. This Sn lie between two fixed values. Suppose say mu and lambda. Okay, lie between two values. Mu lower bound you can say, or lambda is upper bound. So bounded, both side bounded. So this meaning or this meaning. Sometimes it's only use. Next, no problems. Examples on this. One. So this example, for example, I will ask. Show that the sequence Sn where Sn will be 1 upon 1 factorial, 1 upon 2 factorial, 1 upon 3 factorial, 1 upon n factorial. General is convergent. Convergent sequence will be already limit exists, but here other way. So different solution. We note the point. First point, we have always this like 2 in a factorial. So 1 upon n factorial always less than 1 upon 2 raised to power n minus 1. For all the natural number, this condition. So what factorial problem? So 1 upon 1 factorial always less than 1 upon 2 raised to power n minus 1. Okay? In mathematics, 1 point. And second point, I want to show convergent. So convergence means I am here. So convergence, that means monotopic, increasing or decreasing, and bounded. That we show is 2 points. Convergence means monotopic, increasing or decreasing one of them, and bounded sequence. Then it will be a convergence. Okay, so these 2 points I want. So then we start solution. So let Sn be a sequence such that Sn nth term will be this like 1 upon 1 factorial, 1 upon 2 factorial, 1 upon 3 factorial, and so on, 1 upon n factorial. Okay, of course, here will be a natural number. Sn. So I want n plus 1 term also, not only increasing or decreasing. About the n plus 1 term. And n plus 1 terms. So n plus 1 term, one more term. So 1 upon 1 factorial, 1 upon 2 factorial, 1 upon 3 factorial. In this way, 1 upon n factorial. One more extra term is a n plus 1 factorial. Then subtraction, Sn plus 1 minus Sn subtraction. This minus this. Okay, all term cancel except this last term. So 1 upon n plus 1 factorial. Okay, positive? Yes, it is a positive for all the natural number. N equal to 1, 2 factorial, n equal to 2, 3 factorial, 1 upon. So every factorial terms are positive terms, therefore this will be a positive. Okay, so Sn plus 1, Sn is a positive is what? Sn plus 1 will be greater than Sn. Sn plus 1 will be greater than Sn is what? Increasing. So this sequence Sn is increasing, monotonic increasing. So one of them increasing or decreasing. So first find clear. The second point is a bounded lie between. So as of this sequence is like Sn is a factorial 1 upon 1 factorial, 1 upon 2 factorial, 1 upon 3 factorial, 1 upon n factorial. So factorials are always positive. Factorial of every integer is a positive. This is a positive values. Yes, this value will be a positive. That means Sn is positive, is greater than 0. So sequence Sn is greater than 0. I want now less than some values. Okay, less than some values. Now less than, now this. Okay, so as 1 upon n factorial is always less than 1 upon 2 raised to power n minus 1. Use here. So Sn is 1 upon 1 factorial, 1, no problem. After 2 we use n equal to 1, 0. So 1 upon 2 raised to power n equal to 2 factorial, 2. So 2 minus 1, 1 upon n equal to 3. 3 minus 1, 2. 1 by raised to power 3 and so on. And last will be 1 upon 2 raised to power n minus 1. Okay, now this series, this means 2 raised to power 0. Okay, this is a geometrical series. This is a geometrical series. Geometrical series with the first term means A is 1 and common ratio will be 1 by 2. Common ratio, this upon this 1 by 2, this upon this 1 by 2, this upon this 1 by 2. So it's a common ratio. Okay. Then what is formula? Sum formula. Sum of this. Sum will be geometric series. General formula A into 1 minus r raised to power n divided by 1 minus r. Okay. Sum of this formula is like sum formula. So put here. So this will be okay. A first term of the series 1. Common ratio 1 by 2. 1 by 2 raised to power n divided by 1 minus r 1 by 2. So 1 minus 1 by 2, 1 by 2, and this comes to numerator is 2 into 1 minus 1 by 1 raised to power n, 1 by 2 raised to power n. So Sn will be 2 times 1 minus 1 by 2 raised to power n. A natural number. So 1 minus fraction. So this will be less than 2 anyhow. 2 minus something. Okay. 2 minus something will be always less than. So Sn will be less than 2 always. This every term n equal to 1, n equal to 2, okay, any values. But it is a less than 2. So less than 2 already greater than 0. less, okay, greater than 0 and less than 2 means what? Bounded. Sn lie between 0 and 2. So this will be now bounded. So sequence Sn is bounded. Okay, so bounded and I will make already bounded and monotonic. So that means then by theorem, some theorems, it will be convergent. So then this sequence Sn is convergent. Second problem again convergent. Show that the sequence Sn defined by this Sn term will be so 1 upon n plus 1, 1 upon n plus 2, 1 upon n plus 3, 1 upon n plus n. N plus 1, n plus 2, n plus 3 and so on. Each converges So same technique, bounded and totally increasing or decreasing one of them. Increasing always we use. Let Sn be a sequence such that Sn term, n term will be this like. I want n plus 1 as n plus 1. So everywhere in place of n plus 1. So n plus 1 plus 1. N plus 1 plus 2 and so on. It's previous. Okay. N minus 1 and n minus 1. Here n plus n. Yes. Now here also in place of n plus 1, n plus 1 minus 1. N plus 1 minus 1. Here also in place of n plus 1 and n plus 1. So everywhere in place of n plus 1. Now you can subtract here Sn plus 1 minus Sn. So what you see? Okay, this term cancel, this term cancel. Okay, next term. Okay, n plus n, this term cancel. Okay. N twice n minus 2 also this term cancel, previous n plus 2 on this term cancel. Okay, so what you get? Okay, roughly so 1 upon twice n plus 1, what this term are here in the gaps, and this last term not cancel, n plus n twice n plus 2. And okay, first term is n plus 1, starting from here n plus 2, this term we will not cancel, okay, minus n plus 1. Okay, last term n twice n plus twice 2, this in the previous gaps. Okay, you can write here all the terms. Okay. So this term and this term. So 1 upon twice n plus 1. This is 1 by 2 is common. N plus 1 and this 1 times n plus 1. So half times n plus 1 and here 1 times n plus 1. So then half minus 1 minus half. So 1 upon twice n plus 1 minus half times n plus 1. That is very positive. Okay. This value will be positive for all natural number. I will only show positive or negative less than or that term. So positive, if you calculate, computer can be positive. So Sn plus 1 minus Sn will be greater than 0. That means what? Sn plus 1 will be greater than Sn. So greater than increasing. So this will be increasing. So therefore sequence Sn is increasing. Okay, so first point clear, increasing. Now bounded. Okay. Bounded positive as of course is Sn. So 1 upon n plus 1, 1 upon n plus 2, 1 upon n plus 3 or 1 upon n plus n is positive values? Yes, positive clearly. If you put here n equal to any natural number 1, 2, 3 or any values, so this calculation will be positive with chance of negative. So it's positive values. So this Sn will be greater than 0. So will be 0 equal to will be equals to positive. So greater than 0 or less than some term. Is that? Now we have general here. So n plus 1 greater than n? Yes, always. Whatever natural number. Therefore, reciprocal 1 upon n plus 1 will be less than 1 by n? Yes. N plus 2 will be greater than n? Yes, always. For every natural number. Reciprocals 1 upon n plus 2 will be less than 1 by n. So it will be less than, okay, 1 by n, 1 by n, less than 1 by n, 1 by n, 1 by n. Okay. So it is same. So we will put here. So Sn will be equal to this like 1 upon n plus 1, 1 upon n plus 2 and so on, 1 upon n plus n. Put here bigger values. So n plus 1 less than 1 by n. N plus 2 less than 1 by n. N plus 3 less than 1 by n. And so on. So this also n plus n also less than 1 by n. So 1 by n, 1 by n, 1 by how many times? N times. These terms are n times. So n is not only 1. So Sn will be less than 1. Already we know is greater than 0. So Sn greater than 0 and less than 1 is what? Bounded. Lie between two values. So Sn is bounded. So bounded and already increasing. Therefore convergent. Listen. Convergent. Okay, so show increasing sequence and bounded.